this is interesting. If you have two parallel conductors and you send a current through this one and you send a current in the same direction, so the current in this one is in the same direction as the current in this one, what actually happens is they're attracted to each other. Now, for the intuition of that, before I go through using the formulas that show this, here we've got a wire going this direction here, and you can see if it's going in that direction, we can put our thumb in that direction, and we can see that the magnetic, I've drawn in the magnetic field lines are going around there. This one, although it's supposed to be, it's not drawn very clearly, but that one is going in that direction, so it's coming out. So if we remember our rules there, if it's coming out, then my fingers are pointing in the magnetic field for that one, so I've drawn the magnetic field for that one. And if we're going in, the magnetic field is in this direction, so I've drawn them round here. What you can work out is if the magnetic field here are in the same direction, you can actually see that magnetic field is going to be stronger, and it causes it, because that's the case, because you're ending up with a magnetic field that is strong here, tends to push these apart. That's kind of intuitive. You can kind of get a feel for that. I mean, obviously to produce something strong requires energy, yeah, so these two have got to be affected, and obviously it's going to push them apart. Now it's easier if they're going in the same direction, then you can see that magnetic fields then are opposite. So if they're both going in this direction, for the left hand one the magnetic field in this way, and also for the right one the magnetic field is that way, so you can see in the middle they're opposing each other. That means they're matching up, and intuitively you can see that there's less energy to do that, so they tend to be drawn together. So intuitive, you can get a feel that they're going to come together. So when you've got this situation, they're drawn together. Okay, so the two wires are going to be drawn together. So that's the intuition. Now I'll go through my notes and just explain this in using the formulas. So this figure shows segments of two long straight parallel conductors separated by a distance r and carrying currents I and I' respectively in the same direction. Since each conductor lies in the magnetic field set up by the other, each experiences a force. So we can say that they're each experiencing a force from the other. The diagrams show some of the field lines set up by the current in the lower conductor from so here we can see that in this diagram I'm only showing the magnetic fields from the lower conductor. I haven't bothered to show them for the upper conductor. I'm only showing them for the lower. So you can see they're coming round, and here they're coming out again. From this equation here, the magnitude of the B vector at the upper conductor is this. From the equation, F equals I dashed LB, so the force, remember we got this force equation, it's the current times the length times the magnetic field, and that's the magnitude of the force. So using the magnitude of the force, we can then plug in the B value there, and we know what the current is coming in, for example, and over this small amount of length we've got the force. Okay, so the force per unit length, if we divide through by L, we get the force per unit length is this value here. So the right hand rule shows that the direction of the force, so that gives us the force per unit length along this wire. Okay, so now we want to know the direction. The right hand rule shows that the direction of the force on the upper conductor is downwards. So when we working out the force, the convention is to use the palm of our hand. So if we point our fingers in the direction of the magnetic field and our thumb in the direction of the current, then the palm points in the direction of the force, and you can see, so if this magnetic field is going round, caused by this one here, and we've got a current going in this direction, then there's a force pushing that top one down. So that's the other way of showing this intuition here, by actually using this convention of the right hand rule. Okay, so you can see that conductor is being pushed down. An equal and opposite force per unit length acts on the lower conductor, as may be seen by considering the field set up by the upper conductor. Hence the conductors attract. So obviously this one's also going to set up a magnetic field, and it's going to have the same influence on this one. So obviously they're both feeling a force towards each other. If the direction of either current is reversed, the force is reversed also. Parallel conductors carrying currents in opposite directions repel each other. The fact that two straight parallel conductors exert forces of attraction or repulsion on one another is the basis of the official SI definition of the ampere. The ampere is defined as follows. 1 ampere is the unvarying current which, if present in each of two parallel conductors of infinite length and 1 meter apart in empty space, causes each conductor to experience a force of exactly 2 times 10 to the minus 7 newtons per meter of length. So if you set that up and you can measure the force between these two of 2 times 10 to the minus 7, you know you've got an amp. So that's the definition of an amp. So they use this to actually define the amp. So, you know, if you set these all to 1, if you set I to 1, so you set a current of 1 and the other current of 1 and the distance between them as 1, you'll get the F equals 2 times 10 to the minus 7. So you can see where the constants come from. From the definition, from this definition, the ampere can be established in principle with the help of a meter stick and a spring balance. For high precision standardization of the ampere, coils of wire are used instead of straight wires, and their separation is made only a few centimeters. The complete instrument which is capable of measuring currents with a high degree of precision is called a current balance. Note that this definition of the ampere is an operational definition. It gives us an actual experimental procedure for measuring current and defining the unit of current. With this definition, we can now return to electrostatics and define the coulomb as the quantity of charge that in 1 second crosses a section of circuit in which there is a constant current of 1 ampere. Finally, we have to regard the constant K equals 1 over 4 pi epsilon naught in Coulomb's law as an empirical constant determined by experiment. As mentioned earlier, epsilon naught and mu naught are related to the speed of light. This fact provides the most precise determination of epsilon naught. We'll return to this relationship later. Mutual forces of attraction exist not only between wires carrying currents in the same direction, but also between the longitudinal elements of single current carrying conductor. If the conductor is a liquid or an ionized gas, a plasma, these forces result in a constriction of the conductor, as if its surface were acted on by an external inward pressure. The constriction of the conductor is called the pinch effect.